My name is Gilles Lesage, and I am an energy advisor. I am not a mechanical contractor, but as an energy advisor, I've been involved with the LEEP initiatives probably since about 2015. I'm from Kelowna. Again, I'm an energy advisor with Total Home Solutions. Very much involved with step code and LEEP and net zero and so on and so forth over the past many years. And started off with retrofits, so very much well versed, I guess, with what we see out there in regards to some of the houses that you're working with. And so we're hoping to shed some light here on how we can optimize some of the tools and the techniques that are offered up by LEEP. And it's basically to have them offered to you. And so hopefully you can take away today some of these tools that you can use to kind of zero in on a better installation, which in fact will just be better for our clients and homeowners and less callbacks and so on and so forth. Okay, so for today, what we're looking to do is we're going to look at what is an F280 calculation, why should we be using it, and what happens if we use that versus some of the older techniques as well. We'll be looking at sizing considerations for heating and cooling, and of course we're gearing all this towards heat pumps, and considering the temperature dependence of performance. And we're going to talk about dehumidification, and after that we'll be looking at what do we do, how can we get a proper F280 calculation done, and we'll kind of visit a few different ways of doing that might be from room by room to whole house. We're going to explore a few different options there, and some of the synergies that can exist if in fact an energy advisor has been involved with that project already. So what is F280? F280 is, as you all well know, is a CSA standard that is meant to be calculating the heat loss and the heat gains to properly size appliances in homes, namely our heating and cooling equipment. This standard has been around for a long time, and it's actually, as Todd was mentioning, it's in the code. We're supposed to be using this, and now more importantly, the cooling side has been somewhat been focused on a little bit more, just for the fact that with some higher performance houses out there, the solar heat gain and the chance of overheating is becoming something that is more prominent. So we really have to really keep an eye on that, especially kind of in our area in the Okanagan, for example. So why not use this for existing homes as well? It may not be common practice right now, but there's some tools here available that we're going to show you today that will help us use and take advantage of this more precise way of actually sizing systems. What happens if we don't size a system properly? Of course, undersizing is not as prominent as oversizing, but if we undersize a system, obviously we're going to have trouble meeting that heating load and cooling load that is designed for the house. With higher utility costs because we're going to be depending more possibly on that backup system or supplementary system, and of course poor thermal comfort. For oversizing, as we're all well aware, this happens a lot. Sizes are usually being twice, 3 times the size as they should be for homes after we actually have the aha moment of looking at a F280 proper heat loss, heat gain calculation. So again, poor performance. Short cycling and premature wear of equipment is number one. This basically reminds me of my vehicle has the engine off option when you stop at a red light and the engine turns off, which is a great feature to have. In Kelowna, the red lights are timed in a certain way where my engine turns off right when the light's going to turn green again. But that just, in my mind, goes, oh, you know what kind of wear and tear is that doing on my starter, on the engine, for example? So same thing basically with short cycling, with equipment turning on and off more than it should. So that sort of would basically lend to premature failure. Thermal stratification, hot and cold spots in the home, poor dehumidification. If a system is basically cooling off way too quickly, we're not giving the system a chance to get into proper, grabbing some of that moisture out of the air. And of course, we could have noisy systems as well if they're oversized. So as mentioned previously, our case study home located here in Burnaby, 1975, roughly 2,200 square feet. Currently have a gas furnace. And what we're looking to do here, you see here some of the homeowner kind of wants and needs at this point. And our goal today is basically to fill in some of the gaps here with some of the information. So the heating and cooling load, we don't know for this house right now. And then we're also going to be looking how do we, what kind of ducting system is currently in this house and how can we kind of optimize what's already there. Because we're not planning on taking anything out and doing a full, extensive renovation at this point. So sizing considerations for heating and cooling systems for retrofits. We have to keep in mind the temperature dependence of performance when it comes to heat pumps. Here in this graph here, we're showing that at 15 degrees C, there's no need for heating at that point. So the heat pump anywhere below that will be working at its optimal performance. As the temperature cools off outside and the heating load for the home actually starts to rise, obviously the heat pump's going to keep working, but there's a certain point where at the basic, where the need is for the heating load and the capacity of the heat pump, there's a crossover there where it becomes less efficient, where it can't work at 100%. Okay, heat pumps do work, but they can't work at 100% all the time, depending on the outdoor temperature. So what we have to consider here is this balance point right there, where we might need a little bit of supplemental heating, but also towards the left side over here, we also have to consider some of the extremes as well. So when it comes to a backup heating system, we have to consider that we might be below these areas. So all things to consider when you're choosing and sizing that heat pump system along with its backup, either it's built-in or a separate system as well. So here's a graph just showing the energy consumption over the course of a year for this area. So as we can see here, 75% of the heating is basically at above 0 degrees C. So this is during the whole year, the total energy needed for heating the home. So what we're trying to show here is that the heat pump actually, depending on the cutoff temperature, can be pretty well fully responsible for heating the home. It can meet almost all of the needs. Okay, so it's pretty rare that we're going to find some of the needs to be heating below the design temperature. Okay, so less than 2%. Which would be less than -7 degrees Celsius. So just to show that the heat pump actually can handle most of the load here, if not pretty well all of it. Dehumidification, also very important when considering the systems that you're designing and sizing. Basically here, we have to make sure that we don't have too much airflow happening, because at that point the dehumidification process just simply cannot happen. If we can slow down the airflow to like 350 to 400 CFM per ton, you can see what kind of difference that makes here. By reducing the airflow, we're basically increasing the dehumidification by 40%. Okay, so small change there. So what else we can do with that is to size the system properly so that the airflow can be managed in this case so that the dehumidification can happen. So again, oversizing, we might not be in a position to be doing this properly. So our largest opportunity here would be knowing exactly what the heat loss and heat gain is of the home, so we can actually provide a design and a system that operates like it should, that would be improving the thermal comfort and of course the dehumidification. We would lower the utility bills and carbon emissions, and of course a more comfortable system, that delivers more comfort would satisfy our clients and our homeowners and reduce callbacks. So how do we do an F280 calculation? Well, there's a few ways of calculating what might be needed to be installed as part of your quoting or as part of your installs. One is the rule of thumb, and we saw it on the previous question. Or we could just rely on what's already existing in the home. Right now we have it's a 92,000 BTU furnace, okay? That's currently in there. And so, is it good practice to just show up and say, okay, we will put a heat pump in, we're gonna put a heating system in, or maybe, are we gonna replace this furnace with a 92,000 BTU furnace? As you have answered previously with what you thought the heat load might be for the home, just as your first kind of impressions, we're already well below that, right? A room by room F280 analysis is probably the most thorough one We have lots of ways of doing that in regards to software. Tekka Quality First is probably the more prominent one here in British Columbia from my conversations with heating contractors. RightSoft has also been used. HeatCAD, LoopCAD, and of course there's some Excel spreadsheets that are available out there. It is a bit more time consuming, or there's a lot more effort that goes into a room by room heat loss calculation. In some cases, if we have house plans, that eases it a little bit. If we don't, for a retrofit application, we might actually have to take some on-site measurements. We have to have a lot of inputs that go into the spreadsheets and into the software, but it will give us a more accurate number for heat loss and heat gain, and it's also within every space of the home that we're splitting up room by room. Another option is, we'll call it Fast F280. There's a newer, I'll call it newer, system out there that's available called VoltaSnap, and we're gonna have a little demonstration of it. Basically, this works well if an energy advisor has already done an evaluation that has produced a HOT 2000 file. That file can be uploaded into the VoltaSnap software, and it actually will give us a compliant F280 heat loss calculation. But very important to remember, this is a full building heat loss calculation, not room by room, and there's a huge difference there. Okay, even for some jurisdictions, may or may not, they may or may not require the room by room. So some of the bonuses for this is that the energy advisor has already done a lot of the work. Obviously, we've done the takeoffs. It would minimize the work for you, the contractor, if an energy advisor can simply hand you a report for a full block F280 calculation that is compliant with F280, obviously. It does require coordination with the energy advisor and the homeowner. So obviously, these two options would be the best. This is the most thorough one. Here's one that does comply, but it's for full block. And then of course, the old rule of thumb is something that we would rather not see happening as much. Tekka, as mentioned, as from what Todd mentioned, a lot of training available, including a 3-day heat loss, heat gain course, so you can speak to him, and of course go on the website and get some more information on that. A list here of the approved software that is compliant to F280. Again, some of the names that we've already talked about, and as you can see here, the VoltaSnap is in fact on the list, but is not compliant for the room by room. Okay, so when it comes to a full room by room heat loss calculation that you may be performing, if you have the option of speaking with or have a relationship with the energy advisor that may have done an energy audit on this particular house, there's a lot of information there that can be shared, that can be used for inputs for your room by room. And in many cases also, the energy advisors are also properly trained on doing room by room heat loss calculations as well. So a lot of the takeoffs that we do on site, again, are extremely similar to the inputs that go into the, for example, the Tekka Quality First spreadsheet. The only thing that we don't really do as energy advisors is look for ducting that goes through unconditioned space. We might come across it, but we're not out there really looking for it. And that is one of the inputs needed for the F280 room by room. Working with an EA and getting some of this information, obviously, can give you an advantage as well, because there's not a lot of heating contractors that are going to this length of providing a proper information for proper quote and sizing. To our case study home, what we're going to do now is actually fill in the blanks on our heating and cooling loads. So with that said, I'm going to take you just for a little sample of what we can do with VoltaSnap. So usually the energy advisors will have access to this. So it's quite simple. It's an interface that works directly with HOT 2000. You can create a HOT 2000 report in VoltaSnap or bring one in and vice versa. So the first thing we're going to do is actually import this particular HOT 2000 report for our case study home. And that's pretty quick there. We'll create this particular project in VoltaSnap, and here it brings everything in. There's a few modifications that we would have to do is find out what is the CSA F280 weather location? Because that could differ from the HOT 2000 weather location. So that's something that we would have to change. In this case, Burnaby. And once we have that set up, we can go to our top menu, and there's an option here. This just show you how quickly this can be done. We'll run a simulation off this HOT 2000 file. This takes a couple seconds. But with that said, it will actually provide us with a compliant F280 full building heat loss, heat gain, and we could actually, from this, create a report that can be handed in and used as needed. So from there on, we'll go to the F280 tab right there, and boom. It's showing us that we've got a heat loss at roughly 41,000 BTU and a heat gain of roughly 20,500 BTU. Okay, so that's our full block numbers. We can use these numbers. Okay, so with that said, now we can fill in the blanks, and we've got our heat loss and heat gain calculations in there. So with this information, by knowing this, we'll look at the different ways that we can be calculating for the heat loss, heat gain for the home. If we did use existing equipment, obviously, it's a large furnace. So it wouldn't be best practice to actually be installing something of that size. Cooling load right now for this home, we don't have cooling, so we don't know what that is. So if you were to go and use, more of a rule of thumb or going with the existing equipment, it'd be very tough to determine what size of heat pump that would be able to go in here. If we use the rule of thumb, as we're going on the heating side, it might be difficult. You may be using a per square foot or per floor of living space for rule of thumb. Again, it's hard to zero in on a proper way of doing that on the heating side. Cooling side, 1 ton per 1,000 square feet is commonly used. So if we did use that, we'd be at a 2-ton heat pump for our decision making. But if you look at the heat loss, heat gain numbers that we're actually getting, we can really zero in, and at this point, we would see that a 4-ton variable capacity heat pump would be the best fit to cover the loads for this particular home. Okay, so 4-ton would be ideal at this point. There's other considerations too. When we're actually designing and choosing equipment, we got to think about the panel limitations. And we're not going to spend too much time on this because Ben is coming right up to talk specifically about the electrical service provided by the home or available to the home. Ductwork capacity, again, is something else that would be a huge limitation. It'd be good to know what the ducting is capable of doing inside of an existing home so that we could use that information to actually size the system properly. Okay, and we'll be touching on that a little bit before the end of this session. Ceiling heights, it might limit us as to what kind of equipment we could be actually installing. And of course, the outdoor units as well. We might be limited as to how much property we have to actually fit outside equipment. Knowing the actual performance of the ducting system and what it can handle would be a huge benefit, not just above and beyond knowing what the heat load and the design heating and cooling loads should be. So of course, centrally ducted heat pumps will be carrying air that's a bit of a lower temperature, so we have to be able to actually handle that. We need to ensure that the ducts can handle the size of the system that's actually installed as well. The coil also needs to have that airflow go across it so that we have the dehumidification happening. And of course, very important. So how do we calculate or predict the possible airflow so that we can select the best heat pump size? There's a few ways that we can, or one way that we're going to show you. Some of the risks, though, is, again, a lot of the stuff is very familiar here from the first kind of undersizing, oversizing kind of situations, poor comfort, more reliance on the backup system, not enough dehumidification, an uncomfortable home, and of course that would include callbacks as well from your clients. So determining adequate airflow, it's really hard to do that by just looking at the system. We could actually do some measurements and see what it is, but even if we were to do that, the static pressure within the ducting system cannot be calculated by just even taking measurements. the best option is to actually measure the airflow that's happening throughout the duct system. So one way that we were exploring, and as part of this case study, and it's actually still ongoing, is that we were using the Energy Conservatory duct flow equipment and doing that. We've been doing it recently as part of an energy evaluation, just to see how it goes, if it's information that would be useful to contractors, and also to see how feasible it is to include that as a part of your quoting, but also part from an energy advisor's perspective to be part of an energy evaluation on site. So by doing the test on this case study home, we realized that the airflow was at 787 CFM and the total external static pressure at 0.123 water column, which is quite on the lower side. So with this information here, we're able to kind of see what is possible with another heat pump going into this house. So with this information, we know that we have 787, CFM would be optimal, and we have a pretty low external static pressure. So with this, we were able to see that using, fan laws of 400 CFM per ton, we are actually able, for this particular home, to come across with a maximum 5-ton heat pump, because the external static pressure would allow us to get there, because we can go up to about 1-inch water column on that. So again, just with the ducting, we're able to go up to, that'd be the maximum size of heat pump. We're not saying that's the proper size for this, but that is a maximum. So by measuring the duct flow, we can get this information, which is one of the tools on the tool belt to help you choose and select the proper equipment. And of course, anything there, that goes beyond the lower temperatures, our backup system have to be designed to handle that as well.